Hi everyone, this lesson is going to cover 6.5, that's geometric sequences. It is going to follow up on arithmetic sequences, so I am going to assume and take for granted your knowledge that you have studied how to write out explicit formulas, how to do problem set, how to get creative and answer some challenging questions or arithmetic sequences. I'm going to sort of use some parallels and do the same kinds of examples and explanations as I did in arithmetic sequences with geometric sequence, but that means I'm going to go a little bit faster. So hope you're ready. Let's get started. Bust out a paper and pencil. Here we go. Geometric sequence is very similar in arithmetic sequences in that they are a bunch of numbers just like before, separated by commas, of course, and it progressively does something. But take a look at the difference in the definition. A geometric sequence is a sequence where the ratio of consecutive terms is constant. Ratio is sort of like a division, a fraction, so on and so forth. Let me try to explain. Before, for arithmetic sequences, you're able to find the difference by, well, finding the difference. You subtract. It's sort of like doing first differences for a table of values for a linear equation. What if I gave you something like this? Can I stop now? Do you get it? I'm going to stop right there. Okay. What do you notice about this pattern or this puzzle, this sequence? Going once, going twice? Yes, they are all multiples of 2, and it's in fact the first term is basically 2 to the power of 1. The second term is 2 to the power of 2. This third term is 2 to the power of 3. But instead of talking about it just as an exponent, let's talk about it as a sequence. What is happening from the first term as I move to the second term? Well, you're not adding 2, you're multiplying. And then from here to here, I am multiplying. Here to here, I am multiplying. Every term is twice or 2 times the value of the previous term, so on and so forth. Okay. So again, before I sort of go into any more details, let's write out a explicit formula for it. Same numbers, same letters. I want to use the letter A for the first term. And am I using difference right now? No, I'm using a ratio. So what letter can effectively represent ratio? Not rocket science. You don't get any bonus marks. Yes, it is an R. We are going to look at the ratio. What is a common ratio for all these numbers as we progress along the sequence? A 2. The starting value, the first term in this sequence is a 2. And the ratio is also a 2. We start with the first number and we are multiplying it by the ratio. Multiplying it by the ratio, multiplying it by the ratio, multiplying it by the ratio. And we continue to multiply it how many times? Going once, going twice, 1 less than the actual term number. Shall I give you an example? The first term is just A, which in this case is 2. The second term is the starting value, and we multiply it by the ratio, which is 2 times 2. That's a 4. And term 3 is A. We multiplied by the ratio, and then we multiply by the ratio again, which is 2 times 2 times 2. That is an 8. So from term 1 to term 2, I multiplied R once. From term 1 to term 3, I multiplied the R twice. Do you see a connection or a relationship between the term number and how many times we multiply the R value? I hope so, because it's virtually the same as before. Tn is going to be A multiplied by R, 1 less than the term number. This is the explicit formula for geometric sequence. That's it. And of course, just like arithmetic sequence, the types of questions I can ask in the form of a puzzle is pretty extensive. Here are a couple of examples that you may be asked. Okay, I'm going to go straight to, let me draw a line to separate. I'm going to go to page 390. That's example 3. They give you this. There's a 4, there's a 12, there's a 36, ... And the very last term happens to be 2,916. Okay? The question is, determine the number of terms in the geometric sequence. So n equals what? A better way to describe it is, what term number is 2,916? Sort of stumped, aren't you? Well, this is the first time, so I'm going to do this with you. What is the first value? Well, it's T1, which is a 4. What's the R value? Well, you could do the mental math. But do you remember when we did first ratios? Like, if you had this particular pattern on a table of values, let's pretend it's like 0, 1, 2, 3, 4, 5, 6. And this was 1, 2, 4, 8, 16, 32, 64. If you did first differences, you wouldn't get a constant. If you thought, let's do second differences because maybe it's a quadratic, you won't get a constant. And so, me, as your teacher, asked, why don't you try ratios? Instead of subtracting, try dividing. 2 divided by 1 is a 2. 4 divided by 2 is a 2. 8 divided by 4 is a 2. 16 divided by 8 is a 2, so on and so forth. This happened to be a ratio. Same thing here. You want to find the ratio? Take the term divided by the previous term and check if it's constant. Yep. T3 divided by T2 is 36 divided by 12. Yep. And I'm going to assume whatever T4 is divided by T3 is also going to be a 3. The R value is 3. Putting that together, Tn is going to be a r n minus 1. Tn is going to be 4 times 3 to the power of -1, n minus 1. Now we're ready. Let's bring this and this together. Tn, I don't know what that is equal to 2916. But I also know Tn is equal to 4 times 3 to the power of n minus 1. Let's do some algebra. Divide by 4, divide by 4. That gets, let's see, 6, 51, 8, 36, 9 is equal to 3 to the power of n minus 1. Here, you can use this thing called logarithms, but remember I said before, unfortunately, not being part of our curriculum, our department decided we won't actually learn logarithms. Instead, we will give you manageable numbers. I would like you to try and guess and check what that value might be. Okay. Some of you with the calculator might realize I actually made a mistake here. Man, I'm making a lot of mistakes, aren't I? 29 divided by 4, that's 7 with 1 remaining. 11 divided by, that's 3. Nope, that's 2 with 3 remaining, and that's a 9. 329 equals 3 to the power of n minus 1. Sorry about that. So, once again, we will always be giving you manageable numbers that don't require too much guess and check. But take your calculator now, pause the video, and try to figure out 3 to the power of what gives me 729. You try it? I'm going to assume you paused the video and gave it a shot. 729 is the same as 3 to the power of 6. Yes, 3 to the power of 6. So again, sorry for going all over the place. I just ran out of space. So 729 is equal to 3n minus 1. But I just told you 729 is equal to 3 to the power of 6. That means n minus 1 and 6 are the same. So therefore, if n minus 1 equals a 6, that means n must be 7. T7 is equal to 2916. There are 7 terms in this sequence. So again, sort of like puzzles, but I'd like you to give it a try. Please pay special attention to geometric sequences because they naturally connect and make their way towards things like investments and finances. Okay, things like, so basically everything that relates to money. And if you look ahead into chapter 7 and stuff like that, everything is about financial math. Okay, so geometric sequences is basically our future focus. But of course, while we do that, we're also working with arithmetic sequences. Please, please, please pay special attention to this. Do the questions on 393, numbers 1, 3, 4, 8, 9, and 13. I'm not going to stop you from trying more questions. The more you do for geometric sequences, I think the more confident you'll feel as we move towards the future. But that's it. This is geometric sequence. Please practice, and you can expect a kind of problem set on these puzzles sometime soon. Probably after you do arithmetic and geometric series, we'll probably throw something at you, okay, just to make sure you're following through. Practice hard, ask me questions, send me an email, do whatever you need to do. Hope you're healthy, and we'll see you soon.